Welcome back, everyone. This is going to be Unit 1 of AP Physics 1. If you haven't watched my introductory preliminary video, I highly recommend you do that. It contains some prerequisites, some knowledge, some attitudes we should have as we go into this course, and I won't be reviewing what I went over there. Now, time to learn AP Physics 1 from the guy who took and self-studied every single AP exam. So with Unit 1, the title of this unit is called Kinematics. Okay? And the principle of kinematics revolves around three quantities. That is position, velocity, and acceleration. All right, and we're going to do a very deep dive into precisely what each of those are. We're going to be dealing with position on one dimension, which means that we're going to deal with position on something approximating a number line. Okay? One dimension means you're moving along one axis. I can either move forward or backward. We're not dealing with two dimensions yet. We're not going to deal with left and right just yet. We're going to get into that in just a minute. But I want to simplify it down so that we can understand the fundamentals first. Okay? So in any kinematics problem or in any problem in physics, we need to define where zero is. Okay? So in all of physics, you have the discretion to define where your axis is, where your measurements are going to be. So for example, I could define my position right here as 0, okay? And that would mean that that side of the whiteboard is approximately 1 meter forward. It's at the position 1, because position is measured in meters, as I covered in the introductory video. That would be a position 1. Now, alternatively, I could define the axis to say that this side of my whiteboard is going to be 0, okay? So if this side of my whiteboard is 0 and I stand over here, that would mean that relative to my origin, relative to my 0 value, I would be at position -1. I am 1 meter behind my origin, which would, if I draw it out on the one-dimensional axis, if I put 0 here, 1 meter to the right, or 1 meter forward, would be at +1, and 1 meter backward would be at position -1. And you're going to see that that is important because sometimes it's going to be advantageous for you to define 0 at a certain point rather than others. Position can be measured with two quantities. It can be measured either in terms of distance or displacement. So when we change our position, if I walk from position 0 right here, and I walk to 1 meter forward, now I'm at position 1, I have traveled 1 meter. When we talk about distance and displacement, distance here would be a scalar, if we remember that from the introduction. And displacement would be a vector. All right, so let's exemplify how those are different. If I were to travel from my position 0 to my position 1, over here, 1 meter forward, and then I were to travel back to my original position, position 0, the distance I would have traveled 1 meter and then 1 meter. So I would have traveled a total of 2 meters. My distance in that case would have been 2 meters. My displacement, however, given that it's a vector, if I were to travel forward 1 meter and then I were to travel backward 1 meter, you remember how we add vectors? We add vectors tip to tail. So forward 1 meter, backward 1 meter, I start here and I end here. Okay? Therefore, the two vectors cancel each other out, right? Tip to tail. If I go forward and then I add tip to tail and it takes me right back, it means that my displacement is 0. My displacement is 0 because I ended exactly where I began, at position 0. Now, you can also have a velocity. Let's rewrite velocity down here. Velocity can be written as velocity or it can be written as speed. Velocity, in this case, being the vector, and speed, in this case, being the scalar. Okay, so these two words are not interchangeable in the same way that these two words are not interchangeable. I can travel at 1 meter per second this way. I have a velocity of 1 meter per second forward. Again, since this is a vector, it would be specified with the direction, 1 meter per second to the right, or 1 meter per second forward. Speed, being a scalar, is just that. It doesn't have a direction. You would define it as 1 meter per second. The derived unit for velocity or speed would be units of meters per second. Okay? Division bar means that it is a rate of change. Okay? Your velocity or your speed defines the rate at which your position is changing. Okay? If you have a velocity, if you have a speed that are non-zero numbers, it means that your position is changing. If I have a velocity of 1 meter per second, that means I am going 1 meter every second in the positive direction, because it's a vector. If I have a velocity of -1 meters per second, it means I am moving backwards 1 meter per second. I am moving in the negative direction. In one-dimensional space, you can define direction as positive being to the right on the number line or negative being to the left on the number line. So the relationship between velocity and position is that velocity is the rate at which position changes. Okay? And in that relationship, position is the area under a velocity time curve. Now, I went over the velocity time curve in the previous video, but now we can understand what it means. Okay? The area under a velocity time curve would be the displacement during that time. Notice how if I take the area under the curve of a vector, I get a vector. I get the displacement. Let's understand what's going on here in the graph. My velocity is increasing as time passes. That means at time 0, I'm not moving, and as time starts to increase, I slowly start to go faster and faster and faster and faster, which means as time goes on, the distance that I am traveling every second increases because my speed increases as time goes on. Think of it like a race car. When the light is red, the race car is not moving, and the moment the guy swishes the flag and the light goes green, the race car immediately starts speeding up. And it takes time for the car to speed up. So the car is going to, immediately after the light, it's going to start moving slowly, and then is progressively going to get faster and faster and faster until it hits like 100 miles an hour. After velocity, we have the quantity acceleration. Acceleration is the rate at which your velocity changes. Okay? So if we look at a velocity versus time graph, if you remember from algebra, we'd be able to calculate the slope of this graph. All right? And you remember that slope is the rate of change of a graph. So in order to find acceleration, we can find the rate of change of this graph. Okay? So we take one point, let's take the origin, which is 0, 0, and this point, which we're going to call 10, 10, and we're going to realize that the slope m equals 1. Okay? Given that acceleration is the rate of change of velocity and the slope of a velocity time graph is the rate of change of velocity, we can say that our acceleration, in this case, is 1. Okay? And we can also say that the acceleration is constant, meaning the acceleration is not changing, because our slope is the same everywhere on the line. We have a constant acceleration. Since acceleration is the rate of change of velocity, we can then draw another graph, which would be acceleration versus time, and acceleration would be in units of meters per second squared. If we take the area underneath an acceleration versus time graph, then that area would give us our velocity. And the area under a velocity versus time graph would give us our displacement. Now, acceleration is a vector. There is no scalar quantity for acceleration that we will need to be aware of in this course. If you take the area under the curve of a vector, you're going to get a vector. If you take the area under the curve of a vector, you're going to get a vector. Let's try and extrapolate this area under the curve business to interpret a more complex graph. So if I were to give you a graph of acceleration versus time, of course, meters per second squared, seconds, this is my graph of acceleration versus time, okay? Let's try and find the area under the curve, okay? Now, this is an interesting concept when we look at area under curves. An area that is above the x-axis is a positive area, and an area that is beneath the x-axis is a negative area. And you can tell just by looking at the graph that I drew for you here, the area here is approximately equivalent to the area here. So if here I have positive A, and here I have a negative A, that means if I add the two together, I'm going to get 0. So that means that if, let's say, this is time equals 0 seconds and this is time equals 20 seconds, that means after 20 seconds, means at this end, after 20 seconds have elapsed, the area under my curve is 0. So what does that mean? It means my velocity at time equals 20 seconds is 0. All right. Now, why do we need to specify 20 seconds? Because the area under the curve changes when you change your time interval. So for example, I could define my interval from 0 to time equals 15 seconds. And so now this is my area. And now my area would be about a positive 1/2 A. And that would be my velocity after 15 seconds. If your velocity is positive, it means your position is increasing, meaning you have a velocity in the positive direction, means you are traveling further forward in the positive direction with respect to your position. And the same principle applies to acceleration. If your acceleration is positive, it means that your velocity is increasing. All right? That's what we mean when we define the relationship of a rate of change. Given that acceleration is the rate of change of velocity, if acceleration is positive, velocity is increasing. Now, common misconception that we need to be aware of. Just because velocity is increasing doesn't mean it's positive. So if I were to draw a graph of velocity that looks like this, where this is our x-axis, the velocity is increasing for the entire time interval graphed. However, the velocity is negative on this interval and positive on that interval. You are not allowed to say that just because your velocity is increasing means it's positive. That's not true. If it's increasing, all that's telling you is that your acceleration is positive. It does not tell you if your velocity is positive. From there, let's move on to calculating average values. So, the normal way that you would calculate an average is you would take all of the different components of a series, like let's say you wanted to find the average amount of apples in each hoop. You would add up all the apples you have and divide it by the number of hoops. And that's how you would find the average number of apples in each hoop. But you can't quite take that approach here because if you're looking at a graph, there is an infinite amount of times at which you could evaluate the graph. You've got time equals 1.0, 1.01, 1.001, 1.0001, and so on and so forth to infinity. So the way we find average values of our different quantities here, position, velocity, acceleration, is we go by area. So let me again give you a graph of, let's say, velocity versus time. So if my graph looked like this, it was horizontal, what does that tell me? It tells me that my velocity is not changing. My velocity is constant at some value y. If I were to find the area of this region from 0 to, let's say, 8 seconds, the area would be our x value times our y value, okay, which would be equivalent to saying base times height, which you are probably more familiar with. Because the x value is our base and the y value is our height. If I want to find the average value of my function, I need to figure out what y is. So I take area and I divide it by x. Area over my x value gives me my y value. Okay? Now let's see how that is applied to non-constant graphs, like this one. That is a triangle. Here, the value of my velocity is not constant, but I want to find its average value. The average value would be like saying, what value of y is this graph most centered around? Like that's not the center. Center is lower down, right around there. But where is my graph centered at? Okay? And the way we find that by this equality. The area of our shape, whatever it may be, equals our x value multiplied by the average y value. This is always true. The area under our curve is equal to the x value multiplied by the average y value. In this case, our y value was constant, so our y value was our average y value. In this case, our y value is not constant, so we would need to find the area of this shape. Area equals base times height over 2, and then we would use this equation. A over x equals our average y value, and we would simply divide by x. So remember how I said b times h is equivalent to x times y. Our area is equal to x times y over 2. A over x equals y over 2. Therefore, this y, representing our final y value up here, for the case of a triangle, y final over 2 equals y average. And you can do that for any shape. Parallelogram, trapezoid. Any shape you see on your graph, you would find the total area under the curve. You would find the total area under the curve, and you would divide that by your x-axis, your x value, your bounds. In this case, that was 0 to 8. So a divided by 8, in this case, would have given you the average y value. If this was 0 to 10, our a divided by 10 would have given us our average y value. That's how we find average value of any function you're given. The area under the curve divided by x gives you average velocity, because sometimes kids confuse this with change in y over change in x, which is slope. Slope is average acceleration if we take the slope of the velocity time graph. And the slope of our position time graph is our average velocity. Okay, so you can find it two ways. If you wanted to find average velocity, you get area under the velocity curve, you divide it by x, that gives you average velocity, or you find the slope of the position time curve, and that gives you average velocity. Slope of velocity gives you average acceleration. Slope of position, often denoted as x, is equal to average velocity. Okay? So, and the reason position is often denoted as x is what I was hinting at earlier. Position can be expressed on multiple axes. So in this case, there's only one direction, there's only one dimension we can express position in. That's the x direction. You can either go forward in the x direction, which is positive, or you can go backward in the x direction, which is negative. On a coordinate plane that has an x and a y axis, you can go forward in the x direction and you can go forward in the y direction, and vice versa, okay? So you can have a position defined in the x direction, or you can have a position defined in the y direction. And a lot of the problems we're going to be looking at in kinematics are going to feature two axes, okay? Same principles, exact same principles I've been describing to you until now, except we express it on multiple axes, which means I can have a displacement of +1 in the x direction and a displacement of +1 in the y direction, okay? They can be considered exclusively from one another, meaning if I only want to consider my displacement in the y direction, it is +1. If I only want to consider my displacement in the x direction, it is still +1. Now my displacement in the y direction has become positive 2, but my displacement in the x direction is still positive 1. The central sort of topic that we're going to be covering here in kinematics are the kinematic equations that you find on your equation sheet. In the introductory video, I had advised you to print out your equation sheet. I sincerely hope you did so because we will be referencing it a lot. And I am going to assume that you have it with you when you are watching said videos. Okay, so your kinematic equations are going to be the equations at the very top of your equation sheet, on the left side in the mechanics section. Let's write them out and let's start to tackle what exactly they mean. At the very top, we have the velocity in the x direction equals the initial velocity in the x direction, denoted by the naught, plus the acceleration in the x direction times time. Okay? So going back to our no find solve, let's pay attention to what values participate in this equation. V sub x, that would be our final velocity after some time has passed. Vx naught would be our initial velocity. And ax would be our acceleration. Now, important note for all the kinematic equations, the first 3 equations on your equation sheet, big note. They assume a constant acceleration. What does that mean? It means if I were to graph acceleration versus time, it would be a horizontal line. It means my acceleration never changes. If you are dealing with a non-constant acceleration, if you are dealing with an acceleration that is changing, you cannot use these equations. However, the equations do not work with a changing acceleration. However, there's a way to circumvent that. If you have a changing acceleration, let's say your acceleration looks like this graph, you are allowed to use these equations if and only if, instead of a sub x, you substitute in the average acceleration. Only then do these equations begin to work. Okay? And the average acceleration can be used in all cases, because in the case of constant acceleration, your average acceleration equals your acceleration for all points. But in the case of non-constant acceleration, you can only plug in the average acceleration into your kinematic equations. Okay? And again, t equals time. All right? That's our first kinematic equation on the equation sheet. So when would we use this kinematic equation? We'd use it when we know 3, but we don't know 1. It's that simple. Okay. Excuse me. Next equation would be our position, x. That's, again, if you were to look on the right side of your equation sheet as to see what each letter is mapped to, x is denoted as position. Specifically, x is used to denote position on the x-axis, in the x direction. So let's write out the equation. Your position in the x direction, or your position in the x-axis, is equal to your initial position in the x direction, plus your initial velocity in the x direction times time, plus 1/2 your acceleration in the x direction times time squared. In this equation, we have a final position, we have an initial position. Now, it's important to note that if we take our final position in the x direction, minus our initial position in the x direction, that gives us the change in position. Okay? That's what the delta symbol means, change in position. Okay, so if I want to calculate displacement, displacement is a change in position, I can say that delta x, which is equivalent to displacement, I can rewrite the equation as such. I can subtract x naught from both sides of the equation, and I'm left with my displacement, which is equivalent to x minus x naught, equals the velocity in the x direction initially, plus 1/2 the acceleration in the x direction, times time squared. Okay, so as I was alluding to before, this only looks at the kinematic variables in the x direction. Alternatively, you could rewrite it the same exact equation, but in the y direction, which would be y equals your initial position on the y-axis plus your velocity your initial velocity in the y direction times time plus 1/2 your acceleration in the y direction times time squared. Okay? So that is an important factor to consider. These deal with your acceleration, velocity, position on an axis. Okay? So if, let's say from your perspective, towards the whiteboard is the positive x direction, meaning if I'm moving backwards, I'm moving in the negative x direction. All right? And the right, where my hand is extending right now, is going to be the positive y direction. Okay? Meaning if I am moving like this, my position in the x direction is not changing at all. Only my position in the y direction. Okay? If I were to move diagonally like this, that would mean that both my x position and my y position are changing. So I would need to calculate both of these forms of the equation in order to solve for a variable at my final position. Okay? And now let's look at the final kinematic equation that we are given here, which would be your velocity in a given direction, could be x or y, as I've just stated. Your velocity in the x direction squared equals your initial velocity in the x direction squared plus 2 times your acceleration in the x direction multiplied by x minus x naught, which I just stated up here is the same as your displacement, is the same as your delta x. So you could rewrite this as your velocity in a particular direction equals your initial velocity in that direction plus 2 times the acceleration in that direction times delta x, or your change in position, or your displacement. I know that was a lot to take in right now. Let's work through one of the most common problems we see on kinematics together, so you guys can get a hang of how we are going to apply this unit. So in order to tackle this problem, we're going to need to take one more look at vectors. All right? So the interesting thing about a vector is it can be what is so-called resolved into components. What the heck does that mean? Let me explain. So, like I said before, a vector is illustrated as an arrow, okay? Now, that arrow could be moving on what is not one of the coordinate axes. So if this is my x-axis and this is my y-axis, my vector is moving in both the x direction and the y direction, all right? Which means it is said to have both x and y components, okay? So with any vector, such as this one, we can construct a right triangle between this vector and the x-axis, or we can construct a right triangle between the vector and the y-axis. I prefer it to look like this, but it's ultimately up to personal preference. Like I said in my introductory video, vectors add tip to tail, okay? Which means a vector that looks like this is the sum of a vector along the x direction and a vector in the y direction, such that if this is vector A and this is vector B, this is vector C. So the purpose of resolving a vector into components is to find A and B given C. If, let's say, I'm given that this arrow represents velocity, A will represent my velocity in the x direction, and B will represent my velocity in the y direction, such that if I add the two vectors, I get my original given velocity vector. This is a simple right triangle problem that you likely covered in your algebra class, okay? If I am given the original velocity vector, again, the magnitude of the vector is equal to the length of the arrow. So if I'm traveling at 25 meters per second, it means the length of the arrow is 25. Okay, so I am given the length of the hypotenuse, C. And I'm trying to find the length of one leg, x, and the length of the other leg, y. All right, and I would be given an angle, in this case, theta. All right, we are going to whip out our sine, cosine, tan functions. Remember SOHCAHTOA? Sine of theta equals our opposite over our hypotenuse. Cosine of theta equals our adjacent over our hypotenuse. Tan of theta equals opposite over adjacent. Okay? So if I were to look at sine, for example, our hypotenuse is C, that is known. Our opposite, in this case, opposite the angle, is y, such that C times sine theta equals y, and our hypotenuse again is C, our adjacent to the angle is x, such that C times cosine theta equals x. So this shows you how that given the magnitude of the vector C, and given the angle of the vector theta, you would be able to find x and y. You would be able to find the component x vector and the component y vector. And of course, to get from x and y back to C, you would simply do Pythagorean theorem. A squared plus b squared equals c squared. Okay, let's get to our problem. If we have a ball and we launch it up at a speed of 20 meters per second, at an angle theta of 30 degrees relative to the horizontal, how far will the ball go? So in this case, I already discerned out all of the values that you're given. I told you the initial velocity, I told you the angle theta, and I told you what we're looking for. We're looking how far will the ball go. We're looking for our displacement delta x. Now here's where defining your axes, defining your zero, defining your origin becomes important, okay? If I'm looking for displacement, delta x, recall that displacement equals our final position minus our initial position. If our initial position, if we were to define that as position 0, if we were to define that as the origin, then our initial position becomes 0. Therefore, we can simplify delta x as to equaling our final position. We can simplify displacement as being just our final position. First part is we're going to need to take this vector and we are going to need to resolve it. We're going to need to break it up into our x and y components. Because what am I looking for? I'm looking for displacement in the x direction. So I'm going to consult my kinematic equations. Recall that your kinematic equations are written on your reference sheet, top left-hand corner, first 3 equations. I'm looking for what can give me displacement. Here, this is the equation that can give me displacement. So what do I need? I need velocity in the x direction. I need time. And I need acceleration in the x direction. My acceleration in the x direction, there is nothing that's going to be changing my velocity. So this is going to be a constant acceleration, all right? There's no friction, and the problem is going to tell you that you can ignore the effect of wind resistance, okay? So if there's no friction, there's no wind resistance, it means we have nothing propelling us forward in the x direction. We have just our initial velocity. In the case of the y direction, however, there is something accelerating you downward. It's called the acceleration due to gravity. The acceleration due to gravity is denoted g. It is a constant, and it is on your reference table, equals 9.81. To make everyone's lives easier, on any AP exam you take, you are allowed to round g to 10. You are allowed to make that round, and that's going to make your life so much easier. Okay? In fact, all of the correct answers on the multiple choice are derived assuming that g equals 10. So you will, in fact, have it easier if you do this. I'm looking for displacement, and I want to find velocity in the x direction. I'm not directly given velocity in the x direction, but I can find velocity in the x direction by resolving this into components. Recall that the sine of our angle gives us the vertical vector, so our velocity in the y direction initially equals 10 meters per second, and our velocity in the x direction initially equals 10 rad 3 meters per second. Let me pull out my calculator. So that gives us 17.32 meters per second. Now I have velocity in the x direction, velocity in the y. Next thing I need is time t. That's not given to me. So what I need to do, I need to find a way to find time t. I'm going to consult a different equation that I have. This equation tells me that my final velocity in the x direction equals my initial velocity in the x direction plus my acceleration times time t. So if I were to try and use that in the x direction, my final velocity in the x direction and my initial velocity in the x direction will be the same because my acceleration in the x direction is 0. So that's not helpful to me. However, we can try it in the y direction. Let's write that out. My final velocity in the y direction equals my initial velocity in the y direction plus the acceleration in the y direction times time t. I have my initial velocity in the y direction. I just derived it out right here. I got that. My acceleration in the y direction, meaning y direction being top down. Guys, what is the acceleration that we all experience pulling us down? It's going to be an acceleration due to gravity, g. And because the acceleration is pulling us in the negative y direction, the acceleration is going to be negative 10. Our velocity in the y direction initially is negative 10. We want to find t. Do we have the final velocity in the y direction? Well, let's look at the path that this ball would follow if we launched it, okay? If the ball's path is going to look like this, it's going to look like an inverse parabola. If we were to go from point A to point B in some time t, it would take t over 2 to get to the middle right here. And the reasons that's true is because we have a constant acceleration. Okay? So, if I know my final velocity in the y direction is 0, and it's 0 because at the very top of the arc, you're not traveling upwards anymore, and at that exact instant, you're not really traveling downwards anymore. So at the very top of the arc, your velocity in the y direction is 0. And we can use that to solve for the half of the time. So we can rewrite that equation as 0 equals 10 minus 10t over 2. 0 equals 10 minus 5t. T equals 2 seconds. Okay? Now we've just solved for our time. Let me go back to this equation. I'm looking for the displacement. I have my initial velocity in the x direction. I now have my time t. I know that the acceleration in the x direction is 0 because there's nothing pushing me along. And I know my time t. So now I can write and solve this equation. I think I just colored in my suit. That's depressing. Anyway, let's write it out. our displacement, delta x, equals vx naught times t plus 1/2 a sub x t squared. Delta x, that's what we're solving for, equals vx naught, 17.32 meters per second, times time, 2 seconds, plus 1/2 0 times t squared. The 0 makes this whole term go to 0. Therefore, delta x equals our initial velocity in the x direction, 17.32 times 2. We're going to, well, I don't need my calculator. It's going to be 34.64 meters. Again, our units agree. 17.32 meters per second times 2 seconds gives us units of meters. And that's how we find the displacement in the x direction. That's how we find how far the ball will go before it lands. Thank you guys for watching.